Okay, welcome back to today's class. So what I'm going to do, I'm going to do some quick revision of what I did yesterday. It's not going to be an elaborate revision. I'm simply just going to remind you what we did yesterday. So if you recall, yesterday we ended up doing your position vector. Of course, we did components and magnitude also. I think these three will be good enough for today's class. Okay. So if you recall what we did, if I consider the three-dimensional space, say this is R3 or XYZ space, and suppose I consider a point P whose coordinates are given by A1, A2, A3, and if I join the origin with P, that is going to give me a vector. This is OP. If I denote it by A, so then you know that the complements, I can write it like this. I can write the vector like this. Okay. And then we also talked about the magnitude or the length of a vector. And in this particular case, the length of the vector, it is denoted by mod A, and it was simply A1 squared, A2 squared plus A3 squared. Okay, so it is in 3 dimensions, and likewise in 2D, you can easily adjust it accordingly. Okay, so now with these attributes at hand, what we can do, now we can move to define standard basis vectors. Okay, so what are the standard basis vectors? Say suppose in XYZ space, what I do, let me consider the points along x-axis, y-axis, and z-axis in such a way that their coordinates are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, fine. So then, what is going to happen in terms of components? The way we define this vector. So then, if I define a vector, say suppose this is the point A, this is the point B, and this is the point C. So if I want to define the position vector, say OA, in terms of components, okay, so then this is simply going to be 1, 0, 0, right? Similarly, my OB, that is going to be 0, 1, 0, and OC vector, it is going to be 0, 0, 1 in terms of components. Fine? Okay? So now, here, you can see that if I consider all these three vectors, if I consider their magnitude, and if I apply this formula, you will see that the magnitude of each of them, your OA, OB, and OC, it will turn out to be 1. Okay? So, such vectors which have magnitude 1, they are called unit vectors. So basically, what we have done, we are getting 3 vectors along x, y, and z axis. And what is the other property of those 3 vectors? They are simply unit vectors. Is it okay? So there is a specific way. Thank you. So there is a specific way of designating those unit vectors along x, y, and z axis, and they are. And always remember, generally, whenever we define or whenever we designate some unit vector, we put a cap above that. Okay, so this one is denoted by this, and this one is denoted by this. Okay, so basically, what we have done, we have defined 3 unit vectors along x, y, and z axis. Okay. So, and these three vectors, they are called standard basis vectors. I'll tell you why. So now, from the definition of vector addition, now if I go back to this vector, so then this vector, if you recall, it was what we did. We simply took a point whose coordinates were a1, a2, a3, right? And we simply, join O with the point P, and we got the vector OP, which was defined as this. Now, if I use the addition property of vector, which I showed you yesterday, probably I'm going to show it to you again today. So this one, I can decompose it as A1, 0, 0 plus 0, A2, 0 plus 0, 0, A3, right? And if again I use the property of vector multiplication, scalar multiplication, so then this I can write as A1, 1, 0, 0 plus A2, 0, 1, 0 plus A3, 0, 0, 1. Okay, so from here you can easily see that this turns out to be simply what I can write. I can write a scalar multiple like this, A1i plus A2j plus A3k. Okay, fine. So you have seen that any vector with known components can be expressed as this. So likewise, if you take any points there in XYZ space, right? If you know and then like say you join that point with the origin. So basically, in other words, you are trying to find out the position vector of that point, right? And then from this, what should I say? Should I say methodology or from this procedure? Okay, from this procedure, we can see that any vector, the position vector of any point in 3D space, it can be expressed in terms of those unit vectors I, j, and k, right? So that means they form a basis which you are going to learn in your linear algebra course in MA 102. Okay, so because any vectors can be expressed in terms of these three, so that is why they are called basis vectors. Okay, and this I, j, k, they are simply standard basis vectors. Okay, I hope the concept of basis vectors is clear to you. Okay, fine. So now this brings me to another concept. Okay, so this was about expressing a vector in terms of the three standard basis vectors. Okay, so now let us consider an arbitrary vector. So suppose I am considering this arbitrary vector. Okay, this initial point is P and terminal point is Q. Okay, terminal point is Q. Okay, fine. So now, suppose I call this vector as A. Okay, so then A is simply PQ. So now, if I want to find out what just a minute, let me try to, okay, anyway, fine. So now the magnitude of A, it is simply denoted by mod A. Magnitude of A is simply denoted by mod A. Okay, so now likewise we saw that you take say OA, I took this length as 1, fine, and you saw that if I consider the point A1, 0, 0, fine, like suppose this is the point A1, okay, so that means this length is small a1, right? Then I was expressing this vector, in fact, OA1 simply as A1i. Okay, so similarly, I can have A2j and A3k, isn't it? So basically, what was happening here? So here, what I was doing, I was drawing a perpendicular from here to the abstract line L, and then if I join this, and suppose this is the point B1, such that this length is A2, fine, and this P, suppose this length is A3, then I mean because this vector again, this is going to give me A to J, likewise this. So A to J, so that means from the equality or equivalence of vectors, this is nothing but A to J, fine. So that means this vector plus this vector. So initial point and terminal point, you get this vector, fine. So this vector is nothing but A1I plus A2J, fine. And finally, initial point, terminal point, which again become initial point. So this plus this is going to eventually give you this vector OP. And you know that LP is nothing but the vector because this length is A3 and you have a unit vector K. So eventually this ends up as A1I plus A2J plus A3K, right? The geometrically, you can easily understand the things better this way, okay? So now, if I consider any arbitrary vector, likewise, suppose this vector is A bar, okay? And suppose there is a unit vector along this vector, which, as I said, I can define it by A cap. So generally, whenever there is a cap, you should know that. I mean, somebody is trying to define a unit vector, okay? So that means if I take the length of the vector as a scalar quantity and multiply it with the unit vector along that, this is going to give me the whole vector, okay? And anyway, so that means if you want to find a unit vector along a vector, so then the unit vector is always defined by d vector divided by its magnitude. Is it okay with everybody? Fine?
Yes,
Okay. Fine. So that brings us to the concept of, although I mean in Stewart book it may not be there because you guys, I mean, you are going to do, I mean, engineering later on. I mean, probably, I don't know. I think from the very first year, I mean, you are going to start, I mean, doing engineering, drawing, all this stuff. Let me introduce you to the concept of resolving a 2D vector into components. I'll come back to 3D vectors later on. And again, let me tell you, I'm going to go a bit slow in my first few classes because the basic concepts will be clear to you. Okay? Fine. So, and in fact, I'm going to do an exercise. I mean, that is why I'm doing it. And you will see that this concept I'm going to use in some later applications also. Okay, fine. Say, suppose I am considering an arbitrary vector. Say it is given by A. Say suppose, sorry, this is the vector A. Okay. So now, suppose I want to resolve the component of this vector along a certain direction, Okay, and I mean, for the sake of simplicity, that particular direction, I may assume that it is along x-axis. Okay, so basically, what I am telling you, say, suppose along this direction, I want to resolve the component of A. So I may consider this to be x-axis. Okay, it may be something like this along this direction. Then I call that x. Okay, it doesn't matter. So let us assume that along a particular direction, it makes an angle theta, and that direction I am calling x. Okay, fine. So now, what I am going to do, of course, in a direction perpendicular to x, and if I consider the initial point of this vector as my origin, right? And I can easily draw the y-axis along that. Okay, so now you know that this length is given by mod of a. Fine. So that means if I draw a perpendicular here, so this length OL, this is simply going to be a cos theta. Fine. And similarly, your this length LP, it is going to be a sin theta. Is it okay with everybody? Fine. As before, if I consider this I cap and j cap as the unit vectors along x and y axis, so then you know that this vector OL, it is going to be given by simply length of OL into a unit vector along this, and similarly this vector LP, it is going to be given by this. Okay, so that means eventually my vector A, which is equal to OP, it is simply OL plus LP, and it is going to be given by mod A cos theta I plus mod A sin theta J. Is it okay with everybody? Fine. So, so in this way, what we can do, we can resolve the components of a vector. Because you remember, if I mean the coordinates of field are A1 and A2, we define them as components, isn't it? Right? So then, if we want to resolve the components along a particular direction, so then you can see that if that direction here I have considered is an x. So even if this was somewhere here, so the measure of your theta would have been different, right? But adopting the same methodology, you would have been able to find out what. So that means your A1 is mod of A cos theta and A2 is mod of A sin theta, isn't it? So you can easily resolve it into components. Is it okay with everybody? Fine. So now let us try one example. And for that, I'm going to go back to my slides so that we can do some kind of revision also here. Okay. Let me do it here. Okay. Okay, so this is what position vector yesterday I had already done. So these we have already done yesterday, and yeah, these are the properties of vector. So these you can easily do. So this is nothing but commutativity. This is associativity. This is the existence of identity. In fact, this is the additive identity, right? This is zero vector. So if you add 0 to any vector, you are going to retain that vector, right? And this is nothing but the existence of inverse kind of. Okay, so you can always find a vector in the opposite direction such that the sum of them is going to give you the 0 vector, right? So these are nothing but distributive properties. Okay, and this is the existence of what multiplicative identity, right? Again, it's distributivity, right? These are, I mean, straightforward. If you see, suppose if you have to prove all these, properties, so what you have to do, you simply take two vectors in terms of its components, okay, and then do the rest, this rest. Okay, so now this is about standard basis vectors. So this I have already described to you. Okay, so as you can see in 2D, what we do, we take the points 1, 0, right? So we take a vector I in such a way that its length is 1, similarly this j is length 1, and in 3D we have an extra component, as you all know, it is k, right? And eventually in 2D, if you have point A1, A2, this can be done like this. And as I have done earlier, in 3D, it can be done like this. Okay, fine. This I have already explained how you go about it. Okay, and this one. So let's come to this particular example. So now you know that. I mean, what was my purpose behind that? Teaching you the resolution of a vector along a particular direction, resolving the vector into two components. So here there's a question. So what was happening here? A 100-pound weight hangs from two wires as shown in this figure. So now what you have to do, you have to find out the tensions and the forces T1 and T2 in both wires and magnitude of the tensions. Okay. So just by looking at that, it may seem to be a very difficult example, but I mean, you see that now because you have some knowledge about vectors, I mean, through the application of vectors, you can easily do it. Okay, you can easily do it. Okay, fine. So because we have already seen it, so let's try to do it. Okay. Was something like this. I think this was 52. It doesn't matter. I'm going to do in terms of some 32. And there was some 100-pound here. Okay. And then you have to find out the tensors T1 and T2 along this string. Okay. See, basically, you don't need to worry about it. It is something like this. It is something like this. You can see this. So this is a string. This is a string. Okay. So then, what is being done here? Like say, sorry about this clumsiness. Okay. Say, I mean, if this is the weight, this one, it is nothing but a 100-pound weight. So then you will see that as you pull it along this direction and this direction, there are going to be forces. Okay, so those forces are nothing but tensions. Okay, so basically this force along the red pen, it is balancing the tensions. If I define them as vectors, the forces as T1 and T2, they are balancing this weight. Okay, done. So that is exactly what we are going to do. See, okay, fine. So I'm going to call it W, right? So from the figure, you can definitely say that W is equal to T1 plus T2. Okay. So now, if I consider x-axis, I mean considering this to be the origin, the junction of this, junction of the tensions T1, T2, and this weight W as my origin O, and if I consider x-axis along this and y-axis on this, so then, so this is 32. If I call this theta 1, this is theta 1. And if this 52, I call it theta 2. So this angle is going to be theta 2, being opposite angles. Okay. So then, just a minute. Let me call this T1, call this T2, so that I'm consistent with theta 1 to theta. Okay. Fine. So then, what is going to happen? As before, if I want to express T1, so then what is going to happen? As before, this is going to be T1 cos theta 1 I, right? Plus T1 sin theta 1 j. Is it okay with everybody? Fine. And again, remember, if you want to get this vector, it is going to be something like this, and this is in the negative x direction. Okay, and so that is why your T2 it is going to be minus T2 cos theta 2 plus T2 sin theta 2 J. Is it okay with everybody?
Yes,
Fine.
yes.
Fine. Thank you. So now, what is happening out here? What is happening out here? Now you see that this is my y direction. Along y direction, what I do along the positive y direction, I take a unit vector j, right? So that means in the direction of w, right? And the weight is given by 100 lbs, 100 pounds. So this is going to be 100 into minus j. Is it okay? Fine. And since this is going to balance T1 and T2, this is going to balance T1 and T2. So now, if I equate T1 plus T2 with W, what I am going to get? I am going to get T1 plus theta 1 plus, sorry, I think it is minus T2 cos theta 2, this is going to be equal to 0, right? And then T1 sin theta 1 plus T2 sin theta 2, this is going to be equal to what?
W.
Yeah, but W, see, it is
Minus.
minus. Yes, thanks. It is going to be minus. Yes, minus. Okay, fine. So now, see, from here, you can easily express T1 in terms of T2. So this is going to be equal to T2 cos theta 2 by cos theta 1, right? So then what you do, you substitute the value of mod of T1 here, okay? And from there, you'll be able to get the value of mod of T1. Is it okay with everybody? Fine?
Yes,
Okay?
sir.
Yes.
So once you find mod of T1, then with the help of this expression, you can easily find out. Sorry, from here you can find out mod of T2 because you are substituting for T1, right? And once you find out what is the value of mod of T2, you can easily find out mod of T1, right? So then you plug them back in here, and that is going to give you detentions. Detention forces T1 bar and T2 bar. Is it okay? Fine.
Yes, but
So
I have a question.
yes.
Can I ask a question?
Yeah, sure.
How did you write W equal to T1 plus T2?
See, because the weight is going to balance the tensions. Like I showed to you. That is the purpose of this. What I showed to you. Like say, if the pen is the weight. So here, because these two are a bit tight. But if you consider, so suppose you consider a thread, and you hang a weight in the thread, then what is going to happen? The thread is going to exert forces along this direction, in this direction, and this direction, and the weight is going to be below, downward in the vertical direction. Okay, so that is the way the forces are balanced. Is it clear? I think I should have been ready with the rope or something like that. I don't have it. With a rope, it would have been much easier to explain. But you can imagine, you simply think about the thread. You, put a weight at some point in the thread, and then you are going. You'll feel, if you are holding it, you'll feel that it is exerting some pressure in this, some force in this direction and in this direction, right? And where the weight is hanging vertically downwards. So that is exactly this equation. That is where I have got this equation. Okay, right?
Yes.
Okay. So you again, I mean, you guys can go back home and again think back, and because you are going to have my recordings, you can easily work it out. Okay, fine. So this is about the application part. So whatever example is there in the slide, you just simply substitute theta 1 and theta 2 in order to get the exact values. Okay. And this problem is worked out in Stewart form. I mean, you can definitely have a look at that book. Fine. So what do I have? Okay, fine. So now let me come to the concept of dot product. Dot product of two vectors. Okay. So this dot product, it is also called scalar product. I'm going to tell you why it is so. It is also called scalar product. Okay, fine. So let us consider two vectors A. So in terms of component, I can write this. So that means A is simply A1i plus A2j plus A3k, and similarly B in terms of component B1, B2, B3. This is B1i plus B2j plus B3k. So then the dot product of A and B, the vectors A and B, it is written as A dot B, A dot B, and it is simply defined as A1 B1, A2 B2 plus A3 B3. And of course, remember that here the components, they are real numbers. Okay, they are real numbers. These vectors, they are, I mean, 3D vectors. They are 3D vectors. Okay. So now from this expression, you can see that they are simply what? They are simply, this is eventually again, I mean, if all those A's and B's, they are going to be real numbers, it is again a real number, right? So eventually you get only a scalar. Fine. So that is why, see, remember, scalars, I don't think I have defined it earlier. Scalars are nothing but physical quantities, I mean, which has only magnitude. It doesn't have any direction. Okay. So this has only magnitude. So that is why I'm defining it as a scalar. Okay. So that is why the dot product of two vectors, it is also defined as the scalar product of two vectors. Okay, fine. So now, if I operate with the same vector, say if I take the dot product of the same vector, A dot A, then you can see that from this definition, it is simply going to be fine. And what is this? This is simply nothing but the square of the magnitude. Fine. So this property, this particular property, we are going to use, I mean, repeatedly. So again, let me show you the properties. I'm not going to prove it because simply by making use of this definition, you can easily do that. Okay. So let me.
Sir, could you please explain it by geometrically?
Yeah, I'll do that. I'll do that. Definitely, I'm going to do that. Okay, so now you can see here the properties of dot product. This I have already done, and this is obvious because A1 B1 plus A2 B2 plus A3 B3 is simply equal to B1 A1 plus B2 A2 plus B3 A3, and these also you can easily work out. You simply take three dimensional vectors, and then you firstly do this right hand side, and then you do the left hand side. You see that they are going to be equal. Okay, fine. So let me then do the geometrical interpretation. Okay. See, I mean, all these things, I mean, you shouldn't change that because I'm trying to relate, I mean, physics with this concept. You can see that everything is related. Everything is related. All the mathematical things, in fact, they are kind of byproduct of physics or vice versa. Okay? I mean, one cannot survive with the other. Not necessarily physics, everywhere. Chemistry, medicine, economics, sociology, everywhere. That is going to be applied. I mean, that is why I mean, mathematics is called the mother of all sciences. Okay, fine. So now let me go to geometrical interpretation. Geometrical interpretation of dot product. Okay, fine. So now let us consider two vectors, say A and B. Okay, fine. So now again, see, I'm going to do some kind of manipulation here. I'm going to do some manipulations here. Okay, so if we think about vector addition, initial point, terminal point. Again, this terminal point becomes the initial point, and this is the terminal point. So that means this plus this vector, B plus question mark vector is equal to A. Isn't it? Is it okay? Fine. So that means the question mark vector must be the vector. Is it okay?
Yes.
Fine. Okay. Say earlier we saw that your A square is simply A dot A, right? Fine. So now if I want to do what is the square of the magnitude of this vector A minus B, and of course let us assume that the angle between them is theta. Okay, so that means this is simply A minus B dot A minus B. Okay, and if you use the distributive property of vectors, then I mean you can try it at home. So this will turn out to be this minus A dot B minus B dot A plus B dot B. You are going to get this once you expand it. Okay, and again, if I make use of this property, then you can see that this is A square, and because of the what commutative property of vector, because B dot A is equal to A dot B, right? So eventually from these two, I am going to get 2 A dot B, and this is going to give me, fine. Let me call it 1. Let me call this relation as 1. Okay, and then if you use properties of triangle, then you know that if you consider this third side, okay, and the angle between the other two sides is theta. So then again, what we have, the magnitude of the third side is equal to the this minus 2 Is it okay? This you must have studied in geometry. Trigonometry, you must have studied this.
Yes.
Okay?
Yes.
Right? And again, I cannot prove it. I don't have time to prove it. Okay? Fine? So now, if this is 1 and this is 2, and from there, you can easily see that now if I equate this one with this one, because I already have equality of these two, what I am going to get? I am going to get A dot B is equal to mod of A mod of B cos theta. Mod of B cos theta. Okay, fine. So now, so this is the geometrical interpretation of vector dot product. So that means if A and B are two vectors and theta is the angle between them, then A dot B is simply equal to magnitude of A into magnitude of B cos theta. Okay. So from here, you obviously see this product is non-negative. This product is non-negative. This particular product. Okay. So now, if theta is acute, what is going to happen? Your A dot B is greater than 0 if theta is acute. Okay, and then if theta is equal to pi by 2, then A dot B is going to be equal to 0 when theta equal to pi by 2. Okay, and then if theta is obtuse, so then your A dot B is going to be less than 0. Is it okay? Fine. And again, the theta is equal to pi by 2, A dot B equal to 0. So again, if A dot B equal to 0, so then cos theta equal to 0. Then theta must be equal to pi by 2. Isn't it? Or
Yes.
like say, even if you don't want to consider pi by 2, but it is n what should I say? Even if you want to use this expression for some integer n, the angle between them, even then, what is going to happen? The vectors A and B, they are going to be orthogonal. Is it okay? Fine. So that means A dot B
Yes.
equal to 0 if and only if the vectors A and B are orthogonal. Okay? And again, this expression or this geometrical interpretation, it gives me an opportunity to express or to find out the angle between these two vectors in terms of this. So this is simply A dot B, mod of A, mod of B. Okay, and from here, you can simply write theta equal to cos inverse of this mod of A, mod of B. That's it. Okay, I hope now the geometrical interpretation is clear. Okay, fine. What else I have? Okay, fine. How much time do I have? Okay, I still have 10 minutes. Fine. Okay, so if you recall, when we consider a vector in 2D, when we consider the vector in 2D, is right, and then what we were doing, we are trying to resolve its components along x and y axis. Okay, so then we found out that A1, so this is simply cos theta and A2 equal to this sine theta. And remember, this theta is not like the theta of that dot product of two vectors. It is nothing but the angle made by this vector with x-axis. Okay, so that is the way we found it out. So now the thing is that can we extend the ideas or can we expand the ideas to 3D? Okay, how you are going to do this? Is it going to involve both cos theta and sine theta, or is it going to be something different? So that brings me to the concept of direction angles and direction cosines. Okay, so fine. So what we are going to do now, we are going to consider an arbitrary vector in 3D. An arbitrary vector in 3D. Okay? So what we are going to do, we are going to assume that the initial point of the vector is say the origin, and the final point is something like say P. Final point is something like P. Because even if it is not so, suppose the initial and terminal points are initial point is not necessarily the origin. And as you know, yesterday I told you that through parallel displacement, you can always bring the vector towards the origin, okay, so that the origin is going to be its initial point. Okay, so now what I'm going to do, I am going to consider a 3D frame of reference. 3D frame of reference means maybe I should not use that phrase. Let me use the phrase. Let me consider let me consider 3 orthogonal axes at the point O. Okay, fine. So what I am going to do, I am going to rope in, say x, y, and z axis, Let me make it shorter, it will be easier for me to handle it. Okay, at the point O. Okay, and now let us assume that this B it has coordinate A1, A2, A3. Okay, so now let me again assume that this vector OP makes an angle alpha with x-axis. Okay, then just a minute, I should give it direction like this. Okay, alpha with x-axis, beta with y-axis, and gamma with z-axis. So far so good, right? Okay, fine.
Yes.
So now, thank you. Now, as before, let me draw a perpendicular from the point P to the xy plane, and then let me do the earlier. Okay, fine. And then if I consider a unit vector I cap along x-axis, j cap along y-axis, and k cap along z-axis. And again, remember this j cap, by the equivalence or equality of vector, I can consider this also along a parallel line over it, and similarly this one I can consider the unit vector along this direction as well. Fine? Okay. Fine. So then my OP, if I call it simply vector A, it is A1, A2, A3, or this is simply A1I plus A2J plus A3K. Okay, fine. So now you know that along this direction, I mean, if this is the point A, whose coordinates are say A1, 0, 0, fine, and this is the point B, whose coordinates are 0, A2, 0, fine, and what? This is the point C, say, whose coordinates are 0, 0, 8, 3. Fine. So then this vector OA, it is simply A1I. Isn't it? I'm just going to show you one example. Is it okay?
Yes.
Yes, sir.
Right? This vector, if I consider this vector, is simply A1. Fine. So now, if I take the dot product of A1I, okay, which A, then by the definition, in fact, A1I I can simply write as the vector A1, 0, 0. isn't it? Fine. So now if I take the dot product of this with this, so that is going to simply give me what? A1. Okay?
Yes.
Fine. Is it A1 or something else? Just a minute. Just a minute. Rather than doing that,
A1 cos alpha.
no, it is going to give me this I am going to get later on. And see, this concept I can do even without A1, even without A1. Okay, see, let me think about something here. Let me think about the dot product of the unit vector this and A. So that means I am considering this 1 0. That's basis vector. This. Okay. So then what I am going to get, this is simply going to give me, so 1 into simply A1 because the other two components are 0. So this is going to give me A1. Okay. So and again, by the property of dot product, by the geometric interpretation that we had seen earlier. So then this is simply going to be I get this and cos alpha, right? And this is equal to A1. Is it okay with everybody? Fine? Okay? And now
Yes, sir.
I is a unit vector, right? And its magnitude is simply 1, isn't it? Fine? So from here, I am going to get cos alpha equal to your A1 by mod of A2. Is it okay with everybody?
Yes, sir.
Right? So similarly, if I take dot product of j cap with A and k cap with A, so from there, what I am going to get? I am simply going to get cos beta equal to A2 by this and cos gamma equal to A3 by. Fine. So now let us concentrate on these three expressions. These three expressions. Okay. From these three expressions, so let me define what is a direction angle, what are direction angles, and what are direction cosinus. So these three angles, that alpha, beta, and gamma, they are nothing but the angles made by that particular vector, which x, y, and z axis respectively. So they are called the direction angles, and the cosines of those direction angles, that means cos alpha, cos beta, and cos gamma, they are called the direction cosines. Okay, direction cosines of that vector. Okay, this is going to be very, very important later on when we are going to do, the 3D geometry in terms of this vector algebra. Okay, so now, what is the relationship between these direction angles or direction cosines? So now, if you look at these pink encircled, expressions. So from there, if I take the squares of these angles, then you will see that this is simply A3 square. Okay, fine. And what is this?
Mod A square.
Mod is.
Mod A square. So, fine. So this is the relationship between the direction. Is it okay? Fine. So I think we should stop there or no? I still have time. Oh, I didn't know that I'm that fast. Okay, so this is about direction angles and direction cosines. Yeah. So I think I'm going to stop here. So in my next class, I'm going to do vector projection and scalar projection. Okay, and I really thank you all for bearing with me